All right, now there's biaxial stress in torsion shafts, just like there is in pressure vessels. It's the same overall concept. At any time you have these things that we're analyzing, we end up, we can find biaxial stresses for them generally. Now, of course, the equations are a little different, but they're quite a bit different actually. But you know, the idea there is just like with the pressure vessels, we start using those design equations, find stresses in the x and y directions, and then from there we can use biaxial analysis to get inside and find out what's going on at angles. Okay. Now, of course, the equations that we start off with are quite a bit different than pressure vessels. So, you know, the concept is the same, though the equations obviously are not. It's page 620 is where we're at. All right, now when you have a shaft here, and I've got a picture there on 620, looks something like that. What's happening here is you have torsion applied to the shaft. Now that, as we've talked about, that goes right into shear, okay? Because the shear is TR over I, okay? And that's the maximum shear on the outer layer of the shaft. So that's tau max. Well, if you look at how the torsion's applied, you can pretty easily get from that. If you take this torsion right here, kind of curling up, that'll create a shear on that side. This torsion rolling down will create a shear on this side. So we get the shears right on the edges there. And then the other two shears will meet at the corners. So we can get to that shear diagram pretty quickly from the applied torsion. Okay? Just by looking at how those torsions act and how that would affect an element on the outer layer of the shaft. So that torsion on the right rolls up, the one on the left rolls down. The other two meet in the corners. All right. Now, there isn't any normal stresses that are applied directly, so sigma x and y equals 0. So this is kind of like the opposite of a pressure vessel. In a pressure vessel, in the x and y directions, you've got all normal stress and no shear. On a torsion shaft, it's the other way around. You've got all shear but no normal stresses. Okay? And then I have a little note here that'll kind of help you draw the shear on the element based on the torsions on the shaft. So we all right with that? We got any questions on that? All right. Now we can, from there, once we have that established, we can go in and run the biaxial equations. But the thing is that because sigma x and sigma y are both 0, you end up with really simplified biaxial equations. So you end up with these simplified versions of the biaxial equations simply for torsion members, because torsion is a pretty common condition that you run into. And so you use these a fair amount. So they just create special biaxial equations for torsion because they're so much simpler than the full biaxial equations. So here's the equation for normal stress. It's just tau xy sine 2 theta. It's the third term of the full biaxial normal stress equation, okay? Because the other two zero out. And then the shear is just tau xy cosine 2 theta. And that's about it, okay? And that's the second term of the full shear equation. So if you want to figure out the stresses at given angles in a torsion shaft, you use those simplified equations. And they're on the back of the formula sheet under the torsion section. And I'm not sure, there are equations 96 and 97. Okay? So those are specialized biaxial equations, but they're only for torsion because the normal stress in the x and y directions is 0 on a torsion member. All right. Now, again, you might always ask this question, why do I want to know stresses at an angle? Well, a lot of torsion shafts, as it turns out, are hollow. And one way to make those is to take plate and kind of wrap it at an angle. So once again, here's just an example. You might have seams running across your plate. So you might want to know what the stress is on that plane there, okay? Depending on how you fabricated it. So that could be something you might be concerned with. All right, now, of course, we want to know what the maximums are so we can design something. So to find the maximums, what you would do is just be to take these general torsion biaxial equations and maximize them. So the maximum shear will occur when cosine 2 theta maximizes. Well, cosine maximizes when it's 0, when the angle is 0 or 180. So using 2 theta there, it'd either be 0, because 2 times 0 is 0, or you could go 90, okay, because 2 times 90 is 180. So that's how you maximize the normal, or the shear stresses in a shaft. They occur at 0 and 90, and they're just plus or minus tau xy, see? The x and y shear stresses, which are found by TR over I, those are the maximum shear stresses in the shaft, okay? And it kind of makes sense. I mean, that's the biggest one you're going to have. It's right at the 0 degree and 90 degree planes. Now, for the normal stresses, though, that's not the case, because the normal stresses in the x and y directions are 0. So to find the maximum normal stresses, we take this equation and we want to maximize it. So sine 2 theta, that would maximize when the angle 2 theta is either 90 or 270. Half of those, which would be the theta, would be 45 or 135. So the maximum normal stresses occur on the 45 degree planes like that. And as it turns out, they're equal to plus or minus tau xy also. So both the maximum shear and the maximum normal stress are TR over I for a shaft. They just occur on different planes. The maximum shear stress occurs on the 0s and 90s. So right there, like so. The maximum normal stress occurs on the 45 degree planes, maybe something like that. Now, which direction these point on those planes would depend on how the torsion's applied, which direction it's applied, but those would be the basic planes where those maximums occur. So we doing all right with that? Okay. Okay, so that'll about do it here. I don't think we had any homework or anything. So we got all that stuff coming up that's due Friday. We'll cover that tomorrow. Okay. And remember, there's no school on Monday here. I think there is at OSU, but none here. Not OSU either. Okay, so Monday's a holiday, so keep that in mind, okay? Oh, let's see, one other thing too. I guess you guys are all strength, so never mind. There's